Okay, kids, we're back, and we just finished looking at reflection, and now we're going to look at another phenomenon of light called refraction. Refraction. And I'm just going to go through the note that I gave you. I posted this note with your work. Now remember, I've asked you to watch that video first, and then go through this note, and then try the homework questions after you've read the textbook. And this is definitely very much a topic that would require a lot of hands-on in the lab in our classroom, but unfortunately we're not there. We're going to try the best we can to at least have you understand the fundamentals of refraction this time through. So we've got here in the picture someone in a canoe, and what's going to happen is it's probably a sunny day and there's light that's going into the water. So some of the light is going to sink into the water. And as that light goes into the water, it's going to hit the treasure chest. And some of that light that hits the treasure chest is going to reflect off the treasure chest. And light travels in straight lines. So it's going to travel in a straight line until it gets to the boundary between the water and the air. So now the light hits the boundary, hits the air, and when it does that, it refracts. Now, refraction is a scientific term for the word bending. So the light travels in the water, hits the boundary between the water and the air, and bends. And now it has a new direction, and it goes into the person's eye. And the person sees the chest. But the person sees the chest as if it's here. Let's extend this refracted light ray, and it looks to the person as if the the chest is right there. Now you can do a little experiment at home with this. All you need to do is put an object, a pencil, a spoon, a fork, a knife, into a glass of water and take a look at it from above and from each side, and you'll see that depending on where you're looking at it from, that the object will look bent or even broken because of the bending of the light. Now, water and air are different materials that light can travel through. Now, what a scientist would call these materials, it would be a medium. The medium known as water, the medium known as air. Now, not only does the light ray bend as it's going from one medium, one material into another, but the speed of it also changes. Light actually travels more quickly in air than it does in water. And the change in the speed of the light wave is also a big part of the idea of refraction. Now, I'm not reading through the note word by word. This note link is available to you in our daily announcement. Now, the speed of light is the fastest thing in the universe. There's no phenomenon that travels faster than light. Now, the speed of light in emptiness, in the vacuum of space, is 300 million meters a second. Okay, there it is. I've written it down for you. Or in scientific notation, 3.0 times 10 to the 8 meters per second. And in air, it's a little bit less than that 300 million meters per second. And in a material, a medium like glass, it's even reduced more. So look what happens here. Light ray, okay, enters the glass here. So the light here is in air. Here's the boundary between air and the glass. And look, it bends. It doesn't keep its direction anymore. While it's in the glass, it keeps its direction. It doesn't bend while in here. It only bends at the boundary. And then look what happens again. It hits another boundary. Now it goes from the glass back into the air. Look, its direction changed again. So the direction changes, but also the speed changes. The speed of light in the glass is much higher than the speed of light, excuse me, the speed of light in the air is much higher than the speed of the light in the glass. We get refraction, bending, and then the light speed picks up again, starts to speed up again as it leaves the glass and goes back into the air. So not only do we get a change in direction, we definitely get a change in speed. And you would have been doing an experiment very much like this in the classroom. Now, the next thing that scientists wanted to do is actually quantify by how much did the speed change when light enters a particular material. By how much does the light change its direction? How much does it actually bend by when it goes from one material into another? And they started to do experiments with this different materials to see by just how much the speed changed. And what they decided to do is always compare it back to the speed of light in emptiness, in vacuum. And what they decided to do is compare those speeds through a ratio. And here's the ratio right here. The index of refraction of a material is this quantifying of how much the speed changes. And they've decided to call that index of refraction n. So this index of refraction they've called n, and it's just a ratio. The speed of light in a vacuum in emptiness, which we know is 3.0 times 10 to the 8 meters per second, divided by the speed of light in a particular medium or material you're investigating. For example, in the little picture we looked at before, the speed of light in glass is 1.91 times 10 to the 8 meters per second. So you plug in these two speeds into this equation, the numerator, the speed of light in emptiness in a vacuum, the denominator, the speed of light in a material, and each has their own symbol. N, index of refraction, C, speed of light in vacuum, V, speed of light in a particular material. You plug in the values that you know, you do your dividing, and you get 1.57. So now we have a property of glass. It's a characteristic of glass, which is a number. And the number shows us by how much the speed of light changes compared to light traveling through emptiness of space, through a vacuum. So if you take a look here, there isn't much change to the speed of light in air because it's almost equal to 1, right? It's almost equal to 1. So the numerator and denominator here would be very close to the same. When you get into water, you get 1.33, meaning the speed of light in vacuum, C, is greater than the speed of light in the water. By how much? Well, when you divide them, you get 1.33, so it's slowed down some. When you get into something like glass, different types of glass, like plexiglass or flint glass, you're in the 1.5 area, where if you take the speed of light in emptiness in a vacuum and divide it by the speed of light in the material you're investigating, the ratio, and there's no unit to it, right? The meters per second cancel out, is around the 1.5, 1.6. Now this one here is a material called diamond. It's very expensive to buy, trust me. And when you do the ratio here, you get a value of 2.42, which means the numerator, speed of light in vacuum, is quite a bit larger than the speed of light in the material called diamond. It's more than twice. So what this tells us is that diamond really slows down light. And scientists have done experiments, and this is just a partial list. They have these values, the index of refraction, for all the transparent materials that we know, and it's a ratio of the speed of light in vacuum to the speed of light in that material. Very simple division. Now, as we saw in the video and in the little picture I had before, not only does the light uh, slow down, it bends. Bending, the technical word for bending is refract. So here is the incident ray. The light comes in. It's in this material, this medium up here. And what is its direction? Well, the direction is always measured to this imaginary line called the normal. And the normal is 90 degrees to this interface, the boundary between the two surfaces. We've seen the normal when we were doing the law of reflection. So to describe this direction of the light coming in, we tell a person how many degrees is it off of the normal. Then it goes into this new material, it bends, and it bent toward the normal. See, it doesn't continue in this path, it bent toward the normal. And we have the angle of refraction here. It's not theta little I, it's theta big R, the angle of refraction. And you can see here that this angle R is smaller than this angle I. Theta I is bigger than theta big R. So by looking at this, we see that light is moving from a material like air into glass, for example, or air into water. In this case, it's glass. But regardless, it's moving into a material that slows it down and bends it towards the normal. If you were to start the light in the glass, like we did in the picture and you saw in the video, here we reverse the names because now light is coming from in the glass, and this is theta I, hits the interface, hits the boundary, bends, but now the light actually speeds up. So since the light sped up, the light bent away from the normal. Light speeds up, bends away from the normal. Light slows down, bends towards the normal. All right, now this note is in your uh, announcement today. I'm not going to read it word for word. I'm just kind of giving you the highlights here. Now, there was a scientist who wanted to investigate these angles, the angle of incidence, which here is called angle 1, theta 1, and the angle of refraction, which here is called theta 2, and see if there was a relationship between the now established numbers, the index of refraction, right? We just finished talking about index of refraction. And this gentleman named Snell, I think his first name was Willie Broad, Willie Broad Snell, he was able to find this relationship. And this relationship was the following. If you take the index of refraction of the first material, multiply it by the sine of this first angle, it will equal multiplying the index of refraction of the second material multiplied by the sine of the second angle. All right. Now, I don't know exactly where you are in math class, so if you're interested in looking at more deeply in this, I've given an example here. I've given an example here. It's in the link, and you can look at how it's worked out mathematically. But know this much, that there is a law called Snell's law that describes the relationship between the index of refraction for both materials and the angles found in both materials during refraction. So remember, this is 2 days worth of work because it's a pretty long video and I'm doing a whole section here. And when we did reflection with mirrors, I divided that up into two bits, the flat plane mirrors one day, curved mirrors the other day, but we're doing all of this all at once here. So I'm going to give you 2 days to watch that video. I think it's over 40 minutes long, but that company does a good job. And it's the best substitute we have right now for actually doing labs in class because this unit would have been full of hands-on labs, but it is what it is. And You've watched that video. Hopefully you watched this video. You read the textbook. You do the homework. If you have questions, please ask me. Okay, thank you. Bye-bye.